We want to find the limit of the sequence or determine that the limit does not exist. Here we have the sequence 2n minus 1 over the quantity 4 minus 3n. So we're going to apply that theorem we just learned, and we're going to let f of x equal 2x minus 1 over 4 minus 3x. So notice that when we switch to a function, we now use x's instead of n's. So in our sequence we use n, but in our function we need to use x. And now we take the limit of our function. So the limit as x goes to infinity of f of x, which is the limit as x goes to infinity of 2x minus 1 over 4 minus 3x. And here we see that the leading term in our denominator is x. If we remember when we were learning about limits as x goes to infinity from Calc 1, then we want to multiply the top and the bottom by 1 over x. So we are going to find the limit as x goes to infinity of 2x minus 1 over 4 minus 3x. We're going to multiply both the top and the bottom by 1 over x. So now we get the limit as x goes to infinity of 2x minus 1 over x divided by 4 minus 3x divided by x, which equals the limit as x goes to infinity of 2 minus 1 over x divided by 4 divided by x minus 3, which gives us 2 minus 0, because 1 over x goes to 0, over 4 over x also goes to 0, so 0 minus 3, which gives us negative 2/3. So using the theorem we just learned, we can say that the limit as n goes to infinity of a sub n equals negative 2/3 and converges. Here we have the sequence 4n squared plus n minus 1 over the cubed root of 8n to the 6th plus n squared. So in this one, we're going to let f of x equal 4x squared plus x minus 1 over the cubed root of 8x to the 6th plus x squared. And here we see that our leading term, our largest effective power of x, is going to be the cubed root of x to the 6th. So that is x to the 6/3, which is x squared. So we want to multiply the top and the bottom by 1 over x squared when we go to find our limit. So we're finding the limit as x goes to infinity of 4x squared plus x minus 1 over the quantity cubed root of 8x to the 6th plus x squared, and multiply the top and the bottom by 1 over x squared. And this one we're going to rewrite as the cubed root of 1 over x to the 6th. So now we have the limit as x goes to infinity of 4 plus 1 over x minus 1 over x squared over the cubed root of 8 plus 1 over x to the 4th. When we take the limit as x goes to infinity, these terms all go to 0. So we have 4 plus 0 minus 0 over the cubed root of 8 plus 0. So that equals 4/2, which equals 2. So this tells us that the limit as n goes to infinity of our sequence a sub n equals 2 and converges. So here we want to find the limit of the sequence, or determine that the limit does not exist, for n cubed plus 4 over n squared plus 1. So if we let f of x equal x cubed plus 4 over x squared plus 1, so we're looking for the limit as x goes to infinity of x cubed plus 4 over x squared plus 1. So our trick is to look at the highest power in the denominator, which is x squared. So we're going to multiply the top and the bottom by 1 over x squared. So then we get the limit as x goes to infinity of x plus 4 over x squared over 1 plus 1 over x squared. So we see that the x goes to positive infinity, 4 over x squared goes to 0, and 1 over x squared goes to 0. So we're getting that this is infinity, which diverges. This means that we cannot use our theorem to conclude that our sequence also diverges, because remember that if the limit as x goes to infinity of our function diverges, then that does not tell us anything about our sequence. But we can use other methods. We can use a similar method on our sequence. So if we look at limit as n goes to infinity of n cubed plus 4 over n squared plus 1, and we multiply the top and the bottom by 1 over n squared, then we get the limit as n goes to infinity of n plus 1 over n squared over 1 plus 1 over n. So now 1 over n squared goes to 0, and 1 over n goes to 0. So we're left with the limit as n goes to infinity of n divided by 1. So when n is large, our sequence a sub n is about n. So that means that our limit as n goes to infinity of a sub n equals infinity and diverges. Find the limit of the sequence, or determine the limit does not exist, for the sequence cosine of n pi divided by n plus 1. So we're going to let our function f of x be cosine of x pi over x plus 1. So let's consider the limit as x goes to infinity of x times pi over x plus 1. This equals the limit as x goes to infinity of pi over 1 plus 1 over x, which is pi divided by 1, and 1 over x goes to 0, so this limit is pi. So since cosine of u is a continuous function, we get the limit as x goes to infinity of cosine of x times pi over x plus 1 equals cosine times the limit as x goes to infinity of x times pi over x plus 1, which equals cosine of pi, which is negative 1. So that tells us that the limit as n goes to infinity of our sequence equals negative 1 and converges. Find the limit of the sequence, or determine that the limit does not exist, for the sequence inverse tangent of n divided by the natural log of n. So here we have to remember that the limit as x goes to infinity of the inverse tangent of x equals pi over 2, and the limit as x goes to infinity of the natural log of x equals infinity. So if we're looking at the limit as x goes to infinity of the inverse tangent of x over natural log of x, then this has the form a constant k over infinity, which approaches 0. So this tells us that the limit as n goes to infinity of the inverse tangent of n over the natural log of n equals 0 and converges. Find the limit of the sequence or determine that the limit does not exist for the sequence n times sine of 1 over n. So for this one, if we looked at the limit as x goes to infinity of x times sine of 1 over x, we notice that 1 over x goes to 0 as x goes to infinity, and sine of u is continuous. So sine of 1 over x goes to sine of 0, which equals 0. So we're going to have an indeterminate form of infinity times 0. So we want to rewrite this as the limit as x goes to infinity of sine of 1 over x over 1 over x. So now we have the indeterminate form 0 over 0. One thing to note is that we cannot use L'Hopital's rule for sequences. We must use the theorem relating limits of sequences to limits of functions. It doesn't make sense for us to take derivatives of sequences because there are no nearby points, because sequences are a bunch of discrete points. This equals the limit as x goes to infinity of cosine of 1 over x times negative x to the negative 2 power all over negative x to the negative 2 power. So our negative x and negative 2 powers cancel out, and we're left with the limit as x goes to infinity of cosine of 1 over x. And this is cosine of 0. So similar reasoning as up here. 1 over x goes to 0. Cosine of u is continuous, so cosine of 1 over x goes to cosine of 0, which cosine of 0 equals 1. So since the limit of our function is 1, the limit as n goes to infinity of our sequence is 1 and converges. Finding the limit of the sequence, natural log of 3n minus natural log of 7n plus 1, we see that the limit as x goes to infinity of natural log of 3x minus natural log of 7x plus 1 is an indeterminate form of infinity minus infinity. So we're going to rewrite this using logarithms. This is the limit as x goes to infinity of the natural log of 3x over 7x plus 1. Since the natural log of u is continuous on our domain, we have this equals natural log of the limit as x goes to infinity of 3x over 7x plus 1. And this equality is true provided that this limit exists. And the limit of, as x goes to infinity, of 3x over 7x plus 1 equals 3/7. So we have that this equals the natural log of 3/7. So that tells us that our limit as n goes to infinity of our sequence equals natural log of 3/7 and converges. Here we want to find the limit of the sequence, the cubed root of the quantity 1 minus 1 over 4n to the n. So if we rewrite this as a function, we have the limit as x goes to infinity of the cubed root of the quantity 1 minus 1 over 4x to the x. And we can rewrite this as the limit as x goes to infinity of 1 minus 1 over 4x to the x divided by 3. So this is an indeterminate form, 1 to the infinity. So we want to rewrite this. We have an a to the b, and we're going to rewrite this as e to the natural log of a to the b power, which we can then rewrite as e to the b times natural log of a. So we rewrite this as the limit as x goes to infinity of e to the x divided by 3 times natural log of 1 minus 1 over 4x. So now we have a form that is infinity times 0. So now we focus on the inside. X to the third natural log of the quantity 1 minus 1 over 4x, and we're going to find the limit as x goes to infinity of x divided by 3 times natural log of 1 minus 1 over 4x. And now we have an indeterminate form of infinity times 0. So we want to rewrite this as the limit as x goes to infinity of the natural log of 1 minus 1 over 4x divided by 3 over x. So now we have an indeterminate form of 0 over 0. Using L'Hopital's rule, we get the limit as x goes to infinity of 1 over 1 minus 1 over 4x times 1/4 x to the negative 2 power, all divided by negative 3 x to the negative 2 power. So this equals the limit as x goes to infinity of negative 1/12 times 1 over 1 minus 1 over 4x. So 1 over 4x goes to 0 as x goes to infinity. So this limit equals negative 1/12. So this tells us that the limit as x goes to infinity of e to the x divided by 3 natural log of 1 minus 1 over 4x equals e to the negative 1/12. So our sequence limit as n goes to infinity of our sequence equals e to the negative 1/12 and converges. We want to find the limit of the sequence or determine that the limit does not exist, and our sequence is negative 1 to the n divided by n squared. So it's difficult to use f of x equals negative 1 to the x over x squared because negative 1 to the x is not defined for all x using real values. So instead, we're going to use the squeeze theorem for sequences. So we know that negative 1 to the n is between negative 1 and 1 for all n. And n squared is always greater than or equal to 0. So we can divide each part by n squared. So negative 1 over n squared is less than or equal to negative 1 to the n over n squared is less than or equal to 1 over n squared. And this is for all n greater than or equal to 1. And then we look at our sides. So we look at the limit as n goes to infinity of negative 1 over n squared. And that, if we rewrite it as a function, we get the limit as x goes to infinity of 1 over x squared. And we're going to rewrite this as a function. The limit as x goes to infinity of negative 1 over x squared. and this equals 0. And looking at the right side, the limit as n goes to infinity of 1 over n squared, we rewrite that as a function. The limit as x goes to infinity of 1 over x squared, and that also equals 0. So these two are equal. So by the squeeze theorem, we have that the limit as n goes to infinity of -1 to the n over n squared equals 0. We want to find the limit of the sequence 3 plus cosine of n times pi over n plus 1. So we notice that we have a cosine of n times pi, and cosine of n times pi is always between -1 and 1 for all n. So we can add this 3 to each side of our inequality to get 2 is less than or equal to 3 plus cosine of n times pi is less than or equal to 4 for all n. And we also know that n plus 1 is greater than or equal to 1 for n equals 0, 1, 2, etc. So this tells us that we can divide each part of our inequality by n plus 1 without worrying about changing our inequality signs. So we get 2 over n plus 1 is less than or equal to 3 plus cosine of n times pi divided by n plus 1 is less than or equal to 4 over n plus 1 for n equals 0, 1, 2, etc. So now we look at the limit of our sides. So the limit as n goes to infinity of 2 over n plus 1, rewriting this as a function, the limit as x goes to infinity of 2 over x plus 1 is 0. And same with the right hand side, the limit as n goes to infinity of 4 over n plus 1 as a function is the limit as x goes to infinity of 4 over x plus 1, and that also equals 0. So since these two are equal, by the squeeze theorem, we get the limit as n goes to infinity of 3 plus cosine of n times pi over n plus 1 equals 0. And that is by the squeeze theorem. Here we have the sequence n plus -1 to the n over 2n plus 3. So using the squeeze theorem, we're going to start out with -1 to the n is between -1 and 1. So if we add n to each side, we get n minus 1 is less than or equal to n plus -1 to the n is less than or equal to n plus 1 for all n. And we know that 2n plus 3 is greater than 0 for n equals 0, 1, 2, etc. So we can divide each section by 2n plus 3. So n minus 1 over 2n plus 3 is less than or equal to n plus -1 to the n over 2n plus 3 is less than or equal to n plus 1 over 2n plus 3. So now we want to look at the limit of the sides. So the limit as n goes to infinity of n minus 1 over 2n plus 3. And we'll find that this limit equals 1/2, and the limit as n goes to infinity of n plus 1 over 2n plus 3 is also 1/2. So since these are equal, the limit as n goes to infinity of n plus -1 to the n over 2n plus 3 equals 1/2 by the squeeze theorem. Here we have the sequence -1 to the n times n squared divided by n squared plus 1. So starting off, trying to use the squeeze theorem, we get -1 to the n is between -1 and n squared is greater than 0 for n equals 1, 2, 3, etc. So -n squared is less than or equal to n squared times -1 to the n is less than or equal to n squared for n equals 1, 2, 3, and so on. And n squared plus 1 is greater than 0 for n equals 1, 2, 3, etc. So we can divide each part by n squared plus 1. So -n squared over n squared plus 1 is less than or equal to n squared times -1 to the n over n squared plus 1 is less than or equal to n squared over n squared plus 1 for n equals 1, 2, 3, and so on. So finding the limit of the sides, looking at a limit as n goes to infinity of -n squared over n squared plus 1, you find that that is -1. On the other side, the limit as n goes to infinity of n squared over n squared plus 1 equals 1. So these are not equal. So we cannot use the squeeze theorem. If we were to plot some of these terms, we would find that what our sequence does is it gets further and further away. If we were to plot some of these terms, we see that it does stay between -1 and 1, but it doesn't converge to a number. The limit as n goes to infinity of a sub n does not exist and diverges because it bounces back and forth. Here we want to compare growth rates of sequences to determine if the sequence converges. So our sequence that we have, a sub n equals n cubed plus 1 over 4 to the n plus n. So looking for our largest growth rate term, in the denominator, n grows slower than n cubed, which grows slower than 4 to the n. So 4 to the n is our largest growth rate term. So we want to rewrite our sequence as n cubed plus 1 over 4 to the n plus n times 1 over 4 to the n divided by 1 over 4 to the n. So now we have n cubed divided by 4 to the n plus 1 over 4 to the n, all divided by 1 plus n over 4 to the n. So because 4 to the n grows faster than n cubed, this term approaches 0 as n goes to infinity, as does 1 over 4 to the n. And since 4 to the n grows faster than n divided by 4 to the n approaches 0. So if we take the limit as n goes to infinity of n cubed over 4 to the n plus 1 over 4 to the n divided by 1 plus n over 4 to the n, we're going to get 0 plus 0 over 1 plus 0, which is 0. So this converges. Here our sequence is a sub n equals 3n factorial plus 4 to the n over n squared plus n factorial. So comparing our growth rates, we have n squared grows slower than 4 to the n, which grows slower than n factorial. And 3n factorial is in this same class because if you remember from Calculus 1, if the limit as x goes to infinity of f of x over g of x equals a constant, then they're in the same growth rate class. So n factorial is our largest growth rate term. So we have the limit as n goes to infinity of 3n factorial plus 4 to the n over n squared plus n factorial. We're going to multiply the top and the bottom by 1 over n factorial to get the limit as n goes to infinity of 3 plus 4 to the n over n factorial divided by n squared divided by n factorial plus 1. So 4n divided by n factorial is going to go to 0, as does n squared divided by n factorial, since n factorial grows faster. So we're left with 3 plus 0 over 0 plus 1, which is 3. So this sequence converges. Here we have the sequence a sub n equals 5 to the n minus 3 over 7n. So first we need to note that 5 to the n minus 3 is equal to 5 to the n divided by 5 cubed. So we're going to rewrite this as 1 over 5 cubed times 5 to the n. And now we have our limit as n goes to infinity of 5 to the n minus 3 over 7 to the n is equal to the limit as n goes to infinity of 1 over 5 cubed times 5 to the n over 7 to the n. And we can pull the 1 over 5 cubed out in front of our limit. So 1 over 5 cubed times limit as n goes to infinity of 5/7 to the n. So this equals 1 over 5/3 times 0, which is 0, and this converges. So we didn't need to use growth rates with this one, but we're going to use this in a little bit. Let's also look at the sequence b sub n equals n squared sine of n divided by n factorial. Because we see that we have a sine of n, that's kind of a good indication that maybe we want to use the squeeze theorem. So, squeeze theorem, we have negative 1 is less than or equal to sine of n is less than or equal to 1 for all n. So, if we know that n squared divided by n factorial is greater than 0 for n equals 0, 1, 2, etc. So we have negative n squared divided by n factorial is less than or equal to n squared times sine of n divided by n factorial, which is less than or equal to n squared divided by n factorial. So looking at the sides, the limit as n goes to infinity of negative n squared over n factorial, we can use our growth rates for this one. N squared grows slower than n factorial, so that means that this limit is 0. And on the other side, the limit as n goes to infinity of n squared over n factorial, again using growth rates, this one equals 0. So by the squeeze theorem, we have that the limit as n goes to infinity of our sequence b sub n equals 0 and converges. So now let's look at a third sequence. C sub n equals the inverse tangent of 5 to the n minus 3 over 7 to the n minus n squared sine of n over n factorial plus square root of 3. So we just did these two, and we're going to use that. So we have the limit as n goes to infinity of c sub n equals the inverse tangent of the limit as n goes to infinity of 5 to the n minus 3 over 7n minus the limit as n goes to infinity of n squared sine of n over n factorial plus the limit as n goes to infinity of square root of 3. And we can rewrite this, bringing our limits inside, because our inverse tangent is continuous on our domain, and we know that each of these limits exists. So we have that this equals the inverse tangent. We found that this limit was 0, as was the second limit. And the limit as n goes to infinity of square root of 3 is just square root of 3. So the inverse tangent of square root of 3 is pi over 3, and this sequence converges.